Hi, I'm Eric Gepfert from the Weather Company, and I'm presenting with Paula Tashma from IBM Research. My team at the Weather Company is currently working on a re-implementation of our historical weather data API titled History on Demand. Throughout the development process, we've been working closely with Paula and her team at IBM Research so that we can take full advantage of the tools provided by IBM Cloud SQL Query, Cloud Object Storage, and Spark. Today, I'll be discussing History on Demand as a use case for those tools and what my team has learned throughout the development process. Paula will focus on the details of SQL Query and its use of Spark and Spark best practices. This is how we use Spark to serve weather data faster and cheaper. So at the Weather Company, we started with a mission to keep people safe and informed about the weather. Today, the Weather Company has evolved into a decisions and solutions company with data at its core, providing people with the information and the tools they need to make intelligent decisions about the weather. One example of that is History on Demand. This is our historical weather data API, providing access to a global gridded historical weather data set, providing 34 potential weather properties, 34 million records added every hour. We support geospatial and temporal searching. We see on average 600,000 requests per day used by clients primarily for machine learning and data analytics, supporting research in domains such as climate science, energy and utilities, agriculture, transportation, insurance, and retail. So as I said, we're re-implementing History on Demand. Here are some of the problems we set out to solve. First, it was a synchronous API, so that synchronous data access layer was expensive. Additionally, it had limited storage capacity per cluster. And then with those two restrictions, we had to reduce the data we provide to land only and only 20 of the 34 available weather properties. Additionally, because of that synchronous interaction, clients were required to limit the scope of their queries so they would get small amounts of data for each individual query. With those small queries, it took many queries and quite a lot of time to retrieve large amounts of data. So our new solution, with the help of IBM Cloud SQL Query and Cloud Object Storage, has resulted in an order of magnitude reduction in cost. With Cloud Object Storage as the storage solution, we now have an unlimited storage capacity. And with those two limitations out of the way, we now have global weather data coverage, and we make all 34 weather properties available. And we switched to an asynchronous interaction here, so clients can submit a single query for a large amount of data, and then we can process that relatively quickly with the help of SQL Query and Spark behind the scenes. With that, I'll hand it over to Paula to talk a little bit more about the details of SQL Query and Spark.
Here's an overview of our solution. We achieve low cost using a serverless approach. The key point is that compute and storage are separately managed services, which means we don't need to pay for compute when there are no queries. For compute, we use Cloud SQL Query, which is powered by Spark. For storage, we use Cloud Object Storage. And the key advantage of object storage is unlimited capacity at low cost. In addition, we apply best practices such as using Parquet and applying geospatial layout. Cloud SQL Query provides serverless SQL. It has a UI and applications can access it via notebooks using a REST API. We'll show this in our demo. Good performance is challenging when the compute and storage are separately managed. To achieve this, we use data skipping as well as a Hive Metastore. This allows us to skip over irrelevant data, providing high performance and lowering cost. We'll now cover 3 features of SQL Query that are important for our solution. First, the catalog, which is a fully integrated multi-tenant Hive Metastore. This is a best practice whereby a relational database is used to store partition-level metadata. Use of a Hive Metastore is critical for performance for 3 main reasons. Firstly, you can use it to skip irrelevant partitions. This is known as partition pruning. Secondly, it enables listing partitions in parallel. And thirdly, it avoids costly schema inference and enables cost-based optimization. The catalog is also useful for consistently replacing entire partitions, for example, to change their data layout. And we use this capability for history on demand. Now I'll talk about the second feature, geospatial integration. SQL Query boasts a fully integrated geospatial library, which can be used in queries. This library provides geodetic full Earth support, which essentially treats the Earth as round instead of approximating it as flat. This enables more accurate calculations and can be significant, for example, close to the poles. We've integrated the library with our data skipping capabilities. We'll talk about this more soon. Now for the third SQL Query feature, data skipping. SQL Query has a very general data skipping capability, which avoids reading irrelevant objects based on data skipping indexes, which contain aggregate metadata for each object. These indexes are created by users and stored alongside the data in cloud object storage. This complements partition pruning, but at the object level. We support multiple index types, including the standard min-max, but also introducing others, such as value list, Bloom filter, and geospatial index types. To our knowledge, we are the only framework which enables skipping for queries with user-defined function. These UDFs could, for example, be functions from the geospatial library. Under the hood, we have an extensible way to map UDFs to index types, and this is picked up by Spark's Catalyst Optimizer. This goes beyond alternative approaches for data skipping, which are typically based only on min-max and sometimes Bloom filter, and do not support UDFs. So how does data skipping work? Our code is an add-on library which enables the modified query execution flow you see here. On the left is a typical Spark SQL query flow. There's a partition pruning step before reading the data from object storage. We introduce an additional pruning phase which consults object level metadata. This is done using the Catalyst Optimizer and the Session Extensions API. Here's a classic example of data skipping using a min-max index on the temperature column. For each object, we store the minimum and maximum values of that column. When evaluating a query looking for temperatures of over 40 degrees Celsius, Spark with our library will prune the list of relevant objects based on this metadata. In our example, the red objects are not relevant to the query and therefore don't need to be scanned. To build the index, we scan the temperature column once and store the index. From then on, only the index needs to be accessed to make skipping decisions. Note that in the case of Parquet, we also have an optimization which reads min-max metadata from object footers instead of needing to scan the whole column. Since we skip entire objects based on aggregate metadata, it's important to group similar rows together from the point of view of the query workload. We call this data layout. One interesting question is what takes precedence? Should we organize data primarily by time or by geospatial location in the case of our weather data set? This depends, of course, on the workload. For History on Demand, since we expect users to be interested in relatively small geospatial regions and large time windows, we lay out the data accordingly.
So this is how we've applied those best practices to our production data layout. Notice first the two bold lines there beginning with hourly and monthly. These represent the catalog partitions Paula mentioned earlier. How this works is first, for the monthly or for the hourly data, in this case for February, we ingest every hour a full global data set for the previous hour. And then we geospatially partition that into 9 Parquet files. And then we repeat this process once per hour for the month, essentially creating one sort of global layer of data per hour. And then at the end of the month, after all of that hourly data has been ingested, we have a process to sort of relay out that whole month in a single layer with a much smaller geospatially Parquet files. So they take up much less area on a map. And here's what that looks like. So on the left, you can see the hourly 9 geospatially partitioned Parquet files, and then duplicated 744 times in the case of a 31-day month. And then on the right, you see our monthly layout. We've lost the duplication. So now we have single files at any given location. And also notice that we've zoomed in here. So each of those tiles represents a much smaller geospatial area. And back to Paula here.
Now we assume geospatial layout as Eric just described. Here's an example of a query looking for weather data in the Raleigh Research Triangle. Without any optimization, this query would need to scan the entire data set, even when using Parquet or ORC. As you see on the right, we built min-max indexes on the lat and long columns. To enable geospatial data skipping for queries like this, we mapped the ST contains UDF to min-max indexes on these columns. We also did this for the rest of the functions in the geospatial library. An alternative approach, which we also implemented, rewrites geospatial queries by adding additional predicates on the latitude and longitude columns. Once this is done, Parquet and ORC min-max metadata can be exploited. However, not only does this require complex rewrite logic, this still requires reading every object footer for every query. This adds significant overhead because small reads in object storage have relatively high latency. Our approach stores all the metadata together, which reduces the number of reads and increases overall throughput. To show the benefits of consolidated metadata, this is an experiment comparing the data skipping and rewrite approaches for a query like the one in the previous slide. On the x-axis, you see the time window size for the query. As the window size increases, the benefit of having consolidated metadata also increases, until we reached an improvement of 3.6 times faster for a 60-month window. Note that the baseline here already uses the query rewrite optimization. If we didn't use any optimizations, we would need a full scan of the entire data set, since the query involves the UDF. The improvement is a result of avoiding reading Parquet footers and also better resource allocation, because we avoid the situation where Spark allocates a task just to read an object footer and then goes ahead and skips the rest of the object. This experiment is similar, but also takes the catalog into account. Again, our baseline already uses the rewrite optimization, and this is the yellow curve. The blue curve uses both the catalog and data skipping, and we get an average 10-fold speed up across all points in this graph. Again, the data set is in Parquet format. For CSV, JSON, or Avro, the speed up would be much larger. And now for a demo. In this demo, we're going to use Watson Studio notebooks to run SQL Query APIs against the weather company data stored in IBM Cloud Object Storage to do some geospatial analytics. So first I need to log in. I'll pass in my API key. The next step is I'm going to create a table. Here we use SQL Query's built-in catalog to create a table called TWC demo. Now this table is backed by Parquet data in costs. We partition it by year and month, and it has around 40 columns, including latitude and longitude. Then we create the partitions of this table, and we also create data skipping indexes, min-max indexes on both latitude and longitude. So I'm going to skip over those steps because I've done those ahead of time. But now I'm going to go ahead and run the query. So this query gets weather data within a radius of 100 kilometers from New York City for the month of October last year, and calculates the average daily temperature for each location on the grid. So here are our results. We have over 50,000 rows. Note the temperatures are in Kelvin. So now I'm kind of curious regarding the data skipping. How did that work out? So actually we skipped 99.95% of the objects. So this gives a significant boost to performance and reduction in cost. So now you can do whatever you like with this weather data. For example, use it to generate machine learning models and join it with your other data sets. So for this demo, we're going to show an animated heat map of the temperature data for that month. So what this heat map does is it cycles through each day of the month and shows how the temperature in that region evolved over time. So as you can see here in the New York area, temperature is fluctuating on a day-to-day basis. Here are the statistics covering what you just saw in the demo. Creating data skip indexes took just over 12 minutes, and running our geospatial query took just over a minute. Thanks to the use of Parquet, the catalog, and data skipping, the query scanned only 20 megabytes out of the 6.4 terabyte data set.
So here's an example query that we'll be using in production against our data layout. How our API will work here is we'll take requests from a user specifying a location, in this case a bounding box, and a range in time. And then we'll translate that request into a SQL query that will run behind the scenes. In the query here, notice the first half of the where clause, where we're referencing the year-month values from the catalog partitions earlier. What this does is it allows SQL Query to very quickly prune or filter out whole partitions, or in our case, months of data. And then after it finishes that round of pruning, then we move on to the second half of that where clause, where we're referencing the specific timestamp from the request and the location. This first would filter against the metadata that Paula described, and then finally against individual records from the Parquet files. So we did some query performance analysis against our layout. And so this is querying a geospatial area that's 40 grid points by 40 grid points, or roughly 25,000 square kilometers over a range of time, up to, on the high end, 1 year. So in the charts below, you can see hours queried on the x-axis, and notice that both the bounding box query on the left and the radius query on the right are finishing right around 200 seconds. So how does that compare to our previous synchronous solution? With the synchronous solution for querying that same bounding box over 1 year, took 8,000 queries and 2 hours and 15 minutes. With our new synchronous solution, we're down to a single query and only 3 minutes and 20 seconds. A few more comparisons. Again, we have now unlimited storage capacity, global weather coverage instead of land only, all 34 weather properties, unlimited query result size, and all of that with an order of magnitude reduction in cost.
So to conclude, not only did we get order of magnitude cost reductions, we also got performance improvements and enhanced functionality at the same time. Key factors were adopting a serverless approach with Cloud SQL Query and Cloud Object Storage. SQL Query has a powerful geospatial library, fully integrated catalog, and last but not least, geospatial data skipping. Finally, I want to point out that our data skipping work is extensible. It can be applied to other domains other than geospatial, for example, log analytics or genomic data analysis. So thanks very much for listening, and a big thanks to all the team. And don't forget to rate and review this session, and please take a look at our latest blog.